Okay, hi David. I got your email. Figured this would probably be the easiest way to explain the problem to you. So, as I understand it, what you're asking about is an oblique collision, an off-center collision between two identical masses. They don't have to be identical. For the rest of this video, we'll assume that the masses are identical, that energy is conserved, and that there's no addition of any rotational kinetic energy. That is, we're neglecting friction. The arguments should be the same even if we don't make those assumptions, but we'll go ahead and make them. So as I understand it, you are asking about if, say this is ball 1 and this is ball 2, if ball 1 is coming in with some sort of momentum that's completely in the x direction, and at some point over here these balls are going to collide, and after the collision, ball 1 has a y component of its momentum, and ball 2 also has a y component of its momentum. And your question is, if momentum is conserved here in the x direction, that is, if the momentum before and after the collision is the same, where does the y momentum come from? And that's a good question. Although I will say, to start off with, you'd mentioned in your email that if you sum the y momenta components, you come up with exactly, I should say this, 0. And that is very important because in fact there is no y momentum in the system after collision. But I do understand your question. It seems like because there was no y momentum in it first and then there's y momentum afterwards, it sort of comes out of nowhere. So let's see if we can figure out where that comes from. I'm going to shift our perspective just a little bit. So I have the two balls here at the moment of contact, and in the old system, if I can get the right color here, if this is ball 1 and this is ball 2, in the old system we had a momentum that was coming somewhere along this direction. So notice what I've done basically is I have shifted your old axes. I've rotated them through some angle, in this case to the left. So here was your y and your x, and now I'll call this y prime and x prime. So just take your old system and rotate it to the left just a little bit to get our new system. So what I've done, the x prime axis here is actually through the two centers of the ball. And if you know, at the point of contact of these balls, that axis is going to be normal to the surface, to the surfaces of both balls. This is called the line of impact. Sometimes it's also called the line of centers because it goes through the center of each ball. So I'm also going to draw in the momenta after the collision. If I can change colors here. I just downloaded this program, so I'm still learning how to work it. But, no, I don't want that color. Okay, momenta after the collision. In ball 2, the momentum will look something like this. In ball 1, the momentum will look something like this. Now you might ask yourself, how do I know that the momentum of ball 2 is going to be directed along the x prime axis? And to do that, why don't I draw in the action-reaction forces that are going to be experienced by both of these balls. If I can get a better color than that. Okay, so if ball 1 is moving initially, ball 2 is going to experience a force in this direction, and ball 1 will consequently experience a reaction force in this direction by Newton's third law. So to answer the question, how do I know the momentum of the second ball is completely directed along the x prime axis? It's because there's no forces acting on that ball, or any ball, in the y prime direction. So this actually doesn't have a whole lot to do with your problem, but I think it's interesting. Because the forces here are completely directed along the x prime axis, notice that if we examine the balls individually, we find that the momentum for each ball is conserved in the y prime direction. That is, the initial momentum of ball 1, initial in the y prime direction, it's a lot of subscripts, equals the final momentum, final momentum, of ball 2 in the y prime direction. of ball 1 in the y prime direction, and also for ball 2. But that does not happen in your original coordinate system. You cannot make that assumption or that assertion, but in this coordinate system, because we've aligned our forces with the x prime axis, the momentum for each ball is conserved individually. Of course, the total momentum is conserved, but it's just kind of an interesting little way to analyze a problem like this if you have to deal with components. But let me get rid of all that because it's just clouding up the picture. So to explicitly answer your question, the purple vectors are forces, and as we know, no collision actually happens instantaneously. There is a small amount of time that these two balls are in contact. So when we have a situation like that, a force exerted over some time interval, that is going to be defined as the impulse of the collision, and that is a vector. So impulses serve the same function to momentum as a force does to velocity. I should make this force a vector just to be explicit. In other words, a force provides an acceleration which changes the velocity. An impulse changes a momentum. It can change direction, magnitude, what have you, but an impulse is going to provide a change in momentum. And that's actually the answer to your question here. Because notice, if I resolve these impulses into components, I'm going to have, let me get a different color here, I'm going to have, no, yeah, that's what I want. I'm going to have a component, look at number 2, directed along my old x-axis and my old y-axis, like this. And the same with force number 1. I'm going to have a component directed along my old y-axis and my old x-axis. And so if we look in our original coordinate frame, these impulses that I've drawn in here, the small lines in purple, are redirecting the momentum into the y direction of my old coordinate system. So the answer to your question is, where does the y momentum come from? It comes from these impulses. And it's a little confusing because you have to think about switching coordinate systems here. But if you look at the components, I think it'll become obvious that the change in momentum happens because of these impulse components. So your email mentioned energy, and you can talk about conservation of energy here. Even if energy is not conserved, you can talk about energy considerations, because clearly, initially, the kinetic energy is all in ball number 1. Total kinetic energy is all here, the T for total. And after the collision, the kinetic energy is split between ball 1 and ball 2. And in this case, where we're assuming the balls have the same mass, it'll be split equally. But that's not always the case. So it doesn't matter if they have the same mass. All we are saying is the kinetic energy is split up in between both of them. But in this case, I think that's the wrong language to use to talk about this problem, because the natural language of momentum changes is impulse, just like the natural language of velocity changes is acceleration and force. So I hope that clears it up. I'm just about out of YouTube time, so I hope you and Amy are doing good. I'll talk to you later.